So remember, with piecewise functions, you could separate them and say that y equals 3 minus x. You can think of it like that. But it only happens when x is less than 2. So this straight line cuts off once you get to x equals 2. Anything bigger than x equals 2, then you start doing a different behavior. Okay. So this piece is a y equals mx plus b type of thing, right? So it's a straight line. We can make a quick sketch. This isn't necessarily necessary. This isn't necessary if you don't want, but at x equals 2, that's where we're going to stop. So I made sure to label that place. This only happens when x is less than 2. And so this y equals 3 minus x. The y-intercept is 3. And then the slope is -1, which means I count, start on the y-intercept and I count down 1 to the right 1. Down 1 to the right 1. Okay, so there's a sketch of the graph. And then it takes over here, y equals x over 2 plus 1. That starts a new behavior. So to graph this one, the y-intercept's 1, but I'm not going to start my graph here because this is only defined when x is greater than 2. And the slope is 1/2 there, right? You can separate that. It's x over 2, or the same way of saying that is 1/2 x plus 1. So that means I go up 1 and to the right 2. And then that's another dot. But we're not going to fill in that dot because it doesn't say greater than or equal to. I can count on another dot though to help me graph, and now here is where I can start making the connections. Okay, this is an open circle because it's not defined at x equals 2. And then we keep going like this. Okay, I think we're ready to find the points of discontinuity. And again, you don't have to necessarily graph it to do this, but the graph helps you. Discontinuity is where you're tracing it with your finger. You have to lift your finger to get to the next part, and then you've identified a location of discontinuity. X equals 2. That's a point of discontinuity for this piecewise function. So which of these discontinuities are removable? This is not removable. Okay, and a removable discontinuity means it's defined at x equals 2. There's open circles though, because we didn't have a filled in circle. So they're open circles. There's no dot up here anywhere. Solid dot, so it's not removable. Okay. Let's do the next one without a graph. Wait, I think there's one more we're supposed to do. I'll go look for it in just a second. So 21. Let's do this one without graphing. The big thing you're looking for, what's happening when we switch pieces right here at x equals 1. Is that a point of discontinuity? To check it, you want to know what's the limit as x approaches that potential place of discontinuity from the left. And if you're picking a number slightly less than 1, it's this function up here. 1 minus 1 makes 0, and 1 divided by 0 would be undefined. So it's a vertical asymptote here. But if we're approaching 1 from the left, think about a number slightly less than 1, like 0.99999. If we subtract that by 1, and then do 1 divided by a result, we get negative 10 million, right? So this is going to negative infinity. Okay, we usually don't say things are equal to infinity or negative infinity. So the limit approaching 1 from the left is approaching negative infinity. Now the limit approaching x equals 1 from the right means we use this part of the piecewise function because this is where we can be greater than 1. And so this one we don't have to do any funny business because there's no divide by 0 problem. If you plug in 1, you get 1, subtract 2 is negative 1, negative 1 plus 5 is 4. This one we can say it's equal to 4. Okay, those limits don't agree. So that means the limit as x approaches 1 non-directionally does not exist. So if the limit doesn't exist for a certain point, then it's discontinuous. So at x equals 1, this thing is discontinuous. Discontinuous. Which are removable, not removable. This one is not removable because it's not just one dot that's been moved up. Okay, it's a jump discontinuity. If you were to graph both these in Desmos, this one looks like, x equals 1 is the vertical asymptote. It should look something like that. And then this is the graph of a cubic function. I have to work around with it for a bit, but that would look something like this, I guess. Maybe something like that. I guess it's not even technically a jump discontinuity because you have an infinite discontinuity over here. You can't jump over here because you never reach the end at the limit as x approaches 1 from the left. So this is definitely not removable. Okay. Okay, same instructions for this one, except now they've given us a graph. Look, that's a removable discontinuity. When you have a hole and then vertically there's some sort of filled in dot up there. It's a point of discontinuity because the limit as x approaches 0, it does exist. The limit from the left and the right are the same. The limit is 0 because the y values are 0 as you get infinitely close to x equals 0. But the exact value, the non-calculus part where you plug in 0, the piecewise function says, hey, you want x equals 0, then you've got to jump up here. So it's discontinuous at x equals 0. It's also discontinuous over here because if you trace this with your finger, you've got to lift it to jump down here. So it's discontinuous at x equals 1, but it's not removable. Again, a removable discontinuity would be something where you have a filled in dot, a singular filled in dot, and then it can change behavior after that.